Hello, welcome to my channel. Today we are going to be discussing about important topic significant figures in the chapter named Units and Measurement of class 12, sorry, class 11 NCERT syllabus. So let's get started. Significant figures. The name itself suggests significant figure means in the number we are going to consider a significant digits which will make the number very much means in any given number. Let's take 2.356. In this there are four digits. So what are the digits which make significant changes to the value for any measured value? So that's what alphabetical, sorry, in meaning wise it gives. So let's understand this one mathematically how it's moves. First of all, a significant figure is generally defined to a number. Any number, you just ask any given number, what is the significance of this number? What is the significance of a number of 2.5? What are the significant figures of 2.3.26? So that's how the question arises from this topic. So let's be there will be some number for, let's say, for 2.5 there are some two significant figures. For 3.26 there are four. How we are going to see it later. So there are some important note point for these significant figures, which is change of different units does not change significant figures. Means if you say 10 centimeter, and if you say 10 centimeter as 1000, sorry, wait, 10 meter and 1000 centimeter, this both will have the same units. That's what this is saying. Change of unit means if you convert a meter to centimeter, it does not make any difference. So both will have the same significant figure. So just here where we are giving example. This is from NCERT syllabus itself. 2.308 centimeter is equals to 2.0.220 meter, and all have four significant figure. How four we will see later. To find the significant for a number, and here are some important points or the rules for to find significant figures. Let's see one by one. First one, all non-zero digits are significant figures. In any number, all the non-zero digits, there are nine digits, right? 1 to 9, all are significant figures. Then all zeros between two non-zero digits are significant figures. Means any zeros between two non-zero digits, that will be a significant figure. Yeah, no matter where the decimal points in a number, there will be decimal point. No matter decimal point. Next, uh, a number, if a number is less than one, a number is less than 1 in the sense, let's check it out here. It will be something around 0.9 to 0.87, something like that. If the number is less than 1, 0 after the decimal point, means 0 after. Let's take another example where we have zeros. 87064660. So 0 after the decimal before the non-zero digit, third point, are not significant. 0 after the decimal and before the non-zero, this is before the non-zero digit, these are not significant, these are not significant. So then, if number is greater than 1, the number is greater than 1, and terminal zeros are not significant if there is no decimal point. Means there is no decimal point means just like 100 centimeter, 200 meter. In this, these two are not significant. If there is no decimal point and the number is greater than 1, then the zeros, terminal zeros in the sense the last zeros, the end zeros are not significant. Then if n is less than 1, terminal zeros after the decimal point are significant. So in this particular third examples here, you can see the 0 is at the last. So these are the, this is a significant figure. Terminal zeros after the decimal point are significant figures. So if you consider this 0, this is also 0 because this is in between two non-zero digits, which is second point. Second point is saying all zeros between two non-zero digits. So let's take these examples and find the significant figures of these five examples. So here in the first example, 2.012, like all non-zero digits are significant figures. Then 2 is significant figure, 1, 2, these three. And 0 is in between two non-zero digits, so this will be also significant. So there are four significant figures. In second example, uh, all non-zero digits are significant, right? Then look for zeros. 0 is after decimal point and before non-zero, this is not significant. Then 0 after the decimal point, terminal zeros are significant. Kindly see all these points carefully. before you get understand. So this has three significant figures. Next, third example, all non-zero digits are significant and zero between the two non-zero digits are significant. So it has four significant figures. And here, this is significant, this is significant, this is significant. And zero is between 2 and 6. See, that doesn't matter where the decimal point is. If the zero is between the two non-zero digits, then it is always significant figure. So this is also significant, and zero after decimal point terminal zeros are significant. So this has 5. Then last one, here 9 1 2 are significant, 0 these two zeros are in between, so this is significant. And the last one is also significant, so this has 6 significant plus. So I would like to say, please go through all this point carefully and solve more and more problems so you will get understand. Then then there is another important note point here. A multiplying or dividing factor, neither rounded or a decimal point or any measured values, uh, or exact values. Like if you see in this example, let's take this is a formula of circumference, sorry, perimeter, right? Perimeter of a circle. So in this formula, s is equals to pi r. This has no unit, this is just exact number, means 2 is multiplying to pi r. So these kind of numbers which is exact values, which can be written just like 2 or 2.0 or 2.00000, so anything. So this will have an infinite number of significant figures. Infinite number, because zeros after the decimal points are significant, so we can just put any number of zeros, because these two is an exact value. This has no proper definition, like this is just exactly 2 multiply into the pi r. So these kind of values. If you want another example, take some other one, anything like 1 by n into time total t. If n is an integer values, if it is 1 by 2 times of t, here 2 is also an exact value, so 1 by 2 or 2, which has infinite number of significant figures. Then rules for addition and subtraction between two numbers, by considering significant figures. If there is significant figures, then how will you add addition, how will you subtract? Let's see that one. See, there are given, if you have given him three numbers here, just take this example, three examples, and if you want to add these three examples, and what should be the results? How should we represent the results? That's what this is. The rules is all about. So here, your definition says, rule says, results should be retained as many as decimal points as with the least decimal points. Means in the given number, if any number has least decimal point, here in this three example, the second number has only one digit after decimal point. So here two, here three, so the least is this one. So the result after calculating should get one decimal point in the result. So if you calculate, or if you use all this and calculate, there will be a digit and you have to round it up to just 1 8. Okay, this is a perfect answer. Now for rules for multiplication and division. So here, results should be retained with the least significant figures of a given numbers. Let's say we have two given numbers, 1.350 by 1.5. This number has four significant figures, all are significant figures, and 1 and 5 are significant, two significant figures. So if you divide this number by this number, the result would be this. But our answer should be in terms of in two significant figures. So this would be 0.90 as our required answer. Two significant figures. These don't have two significant figures. This number will be in having two significant figures, because it should retain the least number of significant figure. The result. This should be the perfect answer. 0.90 should be perfect answer for 1.350 divided by 1.5. And this round of concept from here to here you can learn. If the last digit is more than or equal to 5, then the preceding term is increased by 1. But here we want to shift it up to here, so let's see about this digit. This is 1, right? So if the last digit is less than 5, if it is less than 5, then preceding term in the sense before term will retain its value, means it will keep on remaining same. The zero will be 0. So 901, if your decimal places to two places, it will be 90. If it is 6, it will changes to 1. So if 2.96, it will changes to 6 will go to here. So it will become 0 and it will become 1. So it will be automatically 3.00. If you want to shift. 3.02 for one decimal places, two decimal places. If we want to shift to 3.6555, this will be 5, right? So it will be shifted and it will become 6. If it is become 6, it is more than 6 and it will become 6, and it is 6 and it will become more than 6, it will become 7. 3.7. So just go through these two statements, you'll understand. Then the most important thing in this chapter, units and measurement, is the dimensions of a physical quantity. This all average all everything in this chapter is comes out to this concept. The motive of this chapter will be in this topic itself, to find the dimension of the physical quantities. We know the fundamental seven quantities. If you have not seen the video, you can go and watch to the previous video where I have uploaded previously, where we have discussed about all seven fundamental units. So those are I just written here all those fundamental units. We have seven units written in the format of bracket. You have to write it in square format. If we are writing for dimensions for physical quantities, any physical quantities, we will come later. We have to write it in the square brackets. So here square bracket L. L in the sense it is for length. It is for length. M in the sense it is for mass. That is mass, and this is the time, and this is current, and this is temperature, and this is intensity, and this is for amount of substance. These are the units we use. So let's say now we have to use for m cube. M in the sense it is length, right? We measure m in length, so distance or length. So m cube will give rise to L to the power of cube. So m cube, you got to write the dimensions of m cube. It will be square brackets inside L to the power of 3. And if you want to write for dimensions of kg square, kg in the sense we represent the mass, so mass has dimensions m, so square bracket capital M square. Similarly, m meter per second, m per second. Actually, this meter per second is a unit of velocity. You can just directly write velocity is equals to m meter per second. So dimensions of velocity will be L and t to the power of minus 1. L is 1 because m is 1, and per second t to the minus. Similarly, if you want to write for m, f is equals to m into acceleration. So m into acceleration will give meter per second square. In fact, m into again meter per second square. So m mass has kg, and this one has m, and this one has kg square. Remember this, don't confuse. This is mass and this is meter. This is mass, this is meter. uh, let's write it in capital A, mass, and this is kg. This is a unit of force. If you want to write dimension formula, kg in the sense it is m. So let's write in the middle, that is, see, always just for standard purpose write in the format of lmt. Okay, don't write mlt. Just to, if you write also no problem, but just keep it lmt format. So m is kg, that is 1, and L is meter, and that is L. Don't confuse it between this m and this is mass, and this is a distance measurement in the meter. So kg is 1, so m is 1, and distance is meter, is n, and seconds is in negative square, so t is equals to. This is the dimension formula for force. Similarly, you can convert any physical quantity in terms of kg, meter, and seconds. Then you can write easily this format. So this is what all about the dimensions of physical quantities, and you can write many more examples. You can go through the NCERT book. There are a lot of examples given, and you can practice those. Now, applications. Applications of dimensions. So, whatever we have discussed here, dimensions, what is the use of these dimensions? Let's see how can this help in our physics. What makes it easier life? Checking the dimension consistency of the equations. So what does that mean? Dimensional consistency means you take any equations. Let's say we have F is equals to mass into acceleration. Okay, not this one. This might be some confusing. Let's start with this equation. This equation is a distance formula. If you might have, you'll come across this equation in second chapter or third chapter of your class 11. This is a distance of a free fall. Okay, here s refers to distance, v refers to initial velocity, and this is time, and this is acceleration, and this is time. Okay, now let's check the dimension consistency of this equation. So what does that mean? Means in equation every term should have the same dimension as the other. So we know for s is a distance, right? That's what I'm saying. So s, distance, in the sense this will have dimension of lmt format. What would be the dimension for s is just distance, right? M. So m, in the sense it will be measuring length. So length will be having 1, m will be having 0, this is 0, that is equals to just l. So s having length l. And by this rule, it should also have ut. This is term, the s is a one term, ut is a one term, of at square is a one term. So now ut, let's take ut. So u is the initial velocity, I'm saying. Velocity we have unit meter per second. So that will have l m 0 and t 1. So we will write l m 0 t minus 1, and t we know that is time, t directly time, that is 1. So this t 1 and minus 1 cancels out, that will give rise to just l, m is 0. So this is also l, this is also l, so it is satisfied. Next, let's get to the third term of at square. Of just is, it is a constant, just leave it. And acceleration we have found earlier, you can go back and see into the video. That is, earlier we found that one, l m t square. Now for t, that is t square. M is 0 for acceleration. uh, Now we get, cancel over this one, t square and t square cancels out, and remaining is l. So all these three terms are giving l. So every equation should satisfy this dimension consistency. If the any equation is not satisfying, then it is not a dimension, like perfect equation. In physics we won't accept it. Every term should have a dimension of l. Okay. Next advantage, you can find like similar way for any different equation. We have another equation in free fall, u plus at. If you calculate for this one also, you'll get the same, like velocity term will have the same dimension, u will be having the same dimension, and at will be having the same dimension. You can verify this one for any equation. Next, second property, second advantages, applications for this, deducing relation among the physical quantities. Let's say now, let's take an example. Deducing equation relation among this, there are a lot of uh, relation given. Let's say here example, in this time is related to k, l, m, g, m. So what are these? Means time means we know this is time, t means time is related to k, where k is a constant, and l means it's a length, and g means it's a mass. Definitely it is in given in gram, and m in the sense it is, sorry, in fact here m in the sense it is mass, and l in the sense it is length, and this one g is an acceleration. This is acceleration due to gravity, which has same unit as a acceleration, that is meter per second square. Okay. Now let's construct equation between these terms. Let's say we, according to the equation, t is related to, directly proportional to k, l, g, m. So considering the first rule, dimension should be equal. So t dimension should be equal to all this combination equation. Let's write dimensions for this particular each term according to the equation. What is the dimension for time? L0, M0, T1. So proportional to k is a constant, so it has nothing to do with, so just cancels. Then L as L, M0, T0. Then acceleration as having m meter square, so it will have L and M0 T minus 2. So m in the sense it is mass, so L0, M1, T0. So it should, right hand side and left hand side should satisfy both. So in this case, what we are getting is, um, let's keep these powers as xyz. Xyz means it is dependent. Let's say xyz means t may be proportional to l square or g cube, m cube. The power should be xyz, so it will be directly multiplied as xyz. So we get l0, m0, t1 is equals to lx, and these are all zeros and it cancels out. Then ly, this is 0 and it's nothing, and t is minus 2y, and here l is 0, m, z, and t is z. So here, again if further lx and y is there, l will be x plus y. L is common and power should be added, so l power of x plus y, and m should be z, and t should be minus 2 to the power of 2 into y. So that is equals to L0 M0 T. So L is equals to 0 means If you compare these equations, L to the power of 0, L to the power of x plus y should be 0. Similarly for m, z is equals to 0. Then minus 2y is equals to 1. If you compare t. So here in this equation we get y is equals to minus 1 by 2. If you put my y value here, you get x is equals to 1 by 2. Y is equals to 1 by 2, x is equals to 1 by 2, and z is equals to 0. So if you apply these values here, what you will get is L0 M0 T directly proportional to sorry, in fact, first equation, sorry. If you consider this equation, T is equals to, if you put that one, K into L is 1 by 2 x value, then G is minus 1 by 2 y value, then M is Z. Z value is just a 0. So we don't need to consider that one. So L is G is 1 minus 1 by 2. It will be K into L divided by G whole to the power of 1 by 2. We can put it down, and common, we are taking power common. So T is equals to this one. We can write this equation in a proper way. T is directly proportional to K into square root of L by G. So this is the formula we have derived from this equation from here. I will explain once again, where T is related to KLGM, where K is a constant, L is a length, and G is acceleration due to gravity, which is unit will be similar to acceleration, that is meter per second square, and M is a mass. So let's take an equation that it has relation between L, G, M in x, y, z format. Means T is directly proportional to L to the power of x, G to the power of y, and M to the power of z. We don't know the value of x, y, z. That's what we are going to find. And dimensions of T will be written as L0, M0, and D. Directly proportional to, we are going to write all these equations similarly to the raised to the power of x and y and z. And if you multiply L to the power of x, it come, and all this doing mathematics, and we get here. So L common, x plus y and m z. To compare the powers between right hand side and left hand side, you get x plus y is equals to 0 and z is equals to 0, and minus 2y is equals to 1, and here y is equals to minus 1 by 2, and if you put here minus 1 by 2, x is equals to 1 by 2. So if you just plot these three values in this equation, you will get T is directly proportional to K, L to the power of half, and G to the power of minus half. And G to the power of minus half goes down. It will be L by G whole to the power of 1 by 2. We can also write this one in terms of this. This is the equation we have derived from this, and this is the advantage of dimension. We can form a relation between given quantities by using dimension formula. Thank you.